Now let's take a look at posterior predictive distributions. These are in contrast to prior predictive distributions that I discussed earlier, right? So what we are going to do now is that, having seen the data, we are going to now generate new data, distributions of new data. So that's what I'm calling Y-pred here, given the observed data, right? So what we are actually going to do is we are going to again integrate out the theta parameters and figure out what new data would look like after we have computed the posterior distributions of the parameters. Remember, when we did the prior predictive distributions, when we generated them, what we did was we sampled from the prior for each parameter, plugged it into the likelihood, and generated, using the R family of functions, generated the simulated data. That was prior predictive data. Posterior predictive data is going to be basically the same story, right? Except that instead of using the priors for the parameters, we are going to use the posterior samples that we get from the model. We're going to plug those into the likelihood and produce future data. That's all this equation is doing, right? And so the code is, of course, very easy. You'll see that in the textbook. I won't show that to you because it distracts from the actual discussion. But really, once you fit the BRM model, you can just generate posterior predictive data using this simple command that's provided with the BRM package, right? It's called posterior predictive check, right? You give as input the actual fitted model with BRM, and you define the number of simulated data points you're producing, and you also define the type of plot that you want to produce. So here I'm providing you with a density overlay plot. The black line, right, is the observed data, so that's the Y, and the blue lines that you're seeing, these are the data sets generated by the model, right? So this was the original model that we fit with the uniform 0-20,000 uniform prior on the mu parameter, okay? And so we are looking at posterior distributions of the data given those prior specifications. And you can see that the model is basically producing reasonable data, right, relative to the observed data. So these are future data sets, simulated future data sets that we are looking at. And if these blue lines had been, for example, out here, just thinking about a pathological case, that would tell you something important about the model, that the observed data and the future data seem to have no connection with each other. Okay, so that's bad news, and that means that there is something wrong with this model. So you would have to go back and think about how to fix that model. Okay, but in this case, we're in the lucky situation that our posterior predictive data fits beautifully, pretty well with the observed data, right? It is slightly more spread out. You see this here, right? The predicted data has a bigger spread, so that's why it's flatter here. But the general shape is similar here. So what happens if I use those very broad uninformative priors? I get a pretty similar fit with the similar predicted data here. Why is that? The reason is that I have a lot of data, and so the priors are not actually having that much of an impact on the predicted data that I'm getting, right? If I had very sparse data, the story might be different, okay? Now, when I use more informative priors, right, you remember the informative priors from the previous lecture, you see that the distribution shifts a bit to the right, right? That I showed that to you earlier, that there was a slight shift to the right in the posterior as well, but the data also has a slight skew to the right, and this is due to the impact of the prior now, the informative prior here, right? And again, when I make the prior principal, that means I make the standard deviation a bit larger. Again, I get this little larger spread and overlap with the observed data. So basically, this kind of posterior predictive check is showing me that all the four priors are reasonable in the sense that they are not going to impact the posterior much, the posterior of the parameters. And I also see that in the posterior predictive data that I'm producing from the model under different prior specifications, right? So this is a way to understand the properties of your model for future data, right? Especially in areas like psychology and linguistics, where we are very interested in replicating, right, our experimental results. Replication is a very important part of doing science, right? So what we want to understand when we've got a particular data set is whether the model that we have chosen for this data set, whether that model is going to produce future data that at least reflects the data that we have, right? This is not a very big achievement because obviously we are conditioning on the data that we already have. So this should not surprise you that we are, in this particular case, pretty close to the observed data, but it is still a good sanity check. And it gives you some idea of the descriptive adequacy of this model, right? And so from the statistical modeling perspective, this is a very useful thing to do. By the way, you can do this in a frequentist model too, but people just don't do it, right? But in the Bayesian modeling framework, this is a standard part of the workflow when you're doing data analysis. Okay, so in summary, what we did here is that we looked at prior predictive distributions. That was also a diagnostic to understand what the model behaves like before it's seen any data, but we also looked at posterior predictive distributions, and these tell us what the model predicts for future data, conditioning on the data that we have actually observed. These are all diagnostic tools for understanding how the model operates and what the predictions and assumptions of the model are, right, in terms of observed data. So what I would suggest is that not during this course, but at some point in the future, you would benefit from reading chapter 6 and chapter 7, where we discuss these ideas in much more detail with many more examples. So the examples help you understand the relevance of these steps, of computing the prior and posterior predictive distributions in the course of doing a data analysis, right? Okay, so now I'm going to show you another model for the same data, where instead of the normal likelihood, which I showed you was somewhat questionable because of the skew in the data, I'm going to use an alternative likelihood, and that's the log normal likelihood. That's the next lecture.